Hello there! Let's get started talking about the properties of water and how water's properties sustain life. Let's begin by picking up with the polarity of water. As we touched on when we first discussed polarity, for something to be considered polar, it must meet all three of these criteria, right? Now, in reference to water specifically, we already touched on the first two criteria in decent detail when we went over the concept of polarity. What I want to focus in more on with you right now is this last criterion, okay? Now, I already told you that the ends of water or of a water molecule have different charges, but how could you have determined this on your own if you were asked? Let's look at that. To figure this out, we need to first address two key questions. Which element is more electronegative, hydrogen or oxygen? And what does electronegativity actually mean? So looking at our periodic table with electronegativities, we see that oxygen is more electronegative, right? 3.5 versus 2.1. Now, what does electronegative actually mean? Electronegativity is an atom's ability to attract electrons towards itself. So looking at the periodic table, we see oxygen has 8 protons while hydrogen only has 1 proton. Remember, protons are positively charged. So between these two hydrogens and the one oxygen that goes into making up the water molecule, the oxygen will pull the hydrogen's electrons towards itself because it's more positive, it's more electronegative. Now, if you are losing a negative charge, that means you are becoming more positive, right? So since oxygen is moving hydrogen's electrons towards itself, or closer to itself, that means that the hydrogens have become slightly more positive because of this, while oxygen has become slightly more negative as it's gaining those electrons. Does that make sense? So circling back, does one end of a water molecule have a different charge than the other end? Yes, right? Where the oxygen in the water molecule has a partial negative charge, and the hydrogens have a partial positive charge, each one of them partially positive. But who cares? How does water's polarity influence its ability to interact with other molecules? Let's think back to magnets. If we have a magnet with positive and negative ends, the positive end will be attracted to the negative end of the other magnet, right? Same for polar molecules. Water can form bonds with other polar molecules, like other water molecules, or even molecules such as ammonia. And it has a high propensity or a high likelihood, therefore, to form hydrogen bonds with other molecules specifically. The reason why understanding water's polarity is so important is because the likelihood of molecules forming bonds and or being able to dissolve in water is based on the polarity of the molecule and the resulting hydrogen bonds that form between water and that molecule. Water is a versatile solvent due to its polarity, which allows it to form hydrogen bonds very, very easily. Now, when talking about a molecule's interaction with water, we refer to them as either hydrophobic or hydrophilic. A hydrophilic substance is one that binds readily with water because it's a polar molecule, just like water. In contrast, a hydrophobic substance is one that does not or cannot interact with water. Hydro, right, meaning water, and phobic, meaning fear, right? Think about phobias. For example, if you have ever dumped oil in water, you've seen how hydrophobic substances like oil can be. Oil molecules are hydrophobic because they are relatively nonpolar. They have relatively nonpolar bonds. They have no partial nor no negative charges on either side. So time for our first check-in within this lesson. Keep in mind, this is check-in number 16. So make sure that you're looking at number 16 when you're filling in your responses, okay? Check-in number 16. Is water polar or nonpolar? And is water more likely to interact with polar molecules or nonpolar molecules? Now, what's so incredible about this, about what we've been talking about, is that because of this very simple interaction that you see, this ability of oxygen and hydrogen to come together and form water, and then water's ability to form hydrogen bonds so easily, because of this, life is able to exist. A water molecule's polar nature is what allows it to form hydrogen bonds so easily. And those hydrogen bonds help sustain life. But how? Well, because of hydrogen bonds, water sticks to things very easily. It helps maintain homeostasis, such as regulating temperatures. It is less dense as a solid as opposed to a liquid. And finally, it is an excellent solvent, meaning it dissolves things very well. Now let's break down why each one of these four aspects, which we attribute to water's propensity to form hydrogen bonds, let's dive into why these are each so important. Let's start with talking about water sticking to things. Have you ever wondered how water climbs up a paper towel if you dip it in water? Or maybe you've wondered how the tops of trees can get water all the way up there, even though the water started all the way down at their roots. And this is despite the forces of gravity working to pull the water downward. Well, it's all thanks to this sticky property of water, which is attributed to the hydrogen bonds that water can form. Water is considered quote-unquote sticky thanks to the forces of cohesion and adhesion. Cohesion refers to the attraction of molecules for other molecules of the same kind. So in this case, that would be water molecules attracted to other water molecules. You can think of it as remembering that the prefix co often means together. So water molecules bonded together is cohesion. Adhesion, on the other hand, refers to the attraction of molecules for other molecules of a different kind. Adhesion is called this because it's referring to things that are adhering to something else. So in this case, that would be water molecules attracted to other substances. And if those substances happen to be polar or have a positive or negative charge to them, then water will cling to those substances really strongly. Fun fact, glass is actually an incredibly polar substance. So if we were to have a glass beaker that is full of water, and then we dropped an open glass tube in that water, water clings to glass so well that we would actually see the water in the beaker travel up the glass tube. This is actually a great model for showing how water and the nutrients water can carry within it are transported to the top of a plant against the force of gravity. Cohesive and adhesive properties are absolutely essential for life. Because of these properties, organisms have fluid transport mechanisms, which is not only important for the movement of water, right? But it's also important for everything that water moves with it, such as our nutrients, vitamins, vital blood plasma, for example. Without this flow, your body's cells would not rehydrate. A communication between your brain and your body would basically slow to a halt, and plants would not have a means for transporting water to the rest of their body from their roots, as just a few examples. So now let's have a very brief check-in seeing if we understand cohesion versus adhesion, okay? So this is number 17, so be careful that you're looking at number 17. Is this example of water droplets sticking to this stem an example of cohesion or adhesion? And number 18, is the formation of the water droplets, so looking at the droplets specifically, is the formation of the water droplets we see here due to cohesion or adhesion? All right, so now let's move on from how hydrogen bonds help water stick to things to discussing how the hydrogen bonds in water help maintain temperature homeostasis. Well, water has a high specific heat and a high heat of vaporization. Looking at specific heat refers to the amount of heat that 1 gram of something must absorb or release to change the temperature of that substance by 1 degrees Celsius. Okay? So consider this. You have a pot of water on the stove. The pot heats up much faster than the water, right? But the same amount of energy, same amount of heat, the same amount of energy is applied to both the pot and the water. So how can this be? Well, every substance has its own specific heat. For example, water, it's 1 calorie per degrees Celsius. And for aluminum, such as like an aluminum pot, it's only 0.2 calories per degree Celsius, meaning less energy is needed to make aluminum hotter. Because water has a high specific heat, that means a lot more heat or a lot more energy is needed to change the temperature of water. So why is this important? The key to all of this is that the high specific heat of water minimizes temperature changes to be within limits that allow life to happen. In short, it helps maintain homeostasis within organisms and their environments. Water's high heat of vaporization also helps achieve this too. Heat of vaporization is slightly different, right? This refers to the amount of heat a liquid must absorb for 1 gram of that liquid to be converted into gas, okay? Vaporization, going from a liquid to a gas, requires breaking hydrogen bonds, which is a process that requires a lot of heat energy. Water has a high heat of vaporization, meaning it absorbs a lot of heat when converting from a liquid to a gas. This property means that we can maintain standing bodies of water on our planet, right? They don't vaporize with solar radiation, for example. That would be disastrous to so many living creatures, right? It is also good because it leads to a process called evaporative cooling. Evaporation is the actual transformation of a substance from a liquid to a gas. So evaporative cooling is the cooling of the surface when water evaporates from it due to all the heat absorbed by water. When water evaporates, though, the hottest water molecules vaporize, leaving the cooler molecules behind. So the high heat of vaporization makes evaporative cooling possible. Evaporative cooling of water helps stabilize temperatures in living organisms and in bodies of water. So now let's transition from maintaining homeostasis to how the hydrogen bonds in water make it less dense as a solid as opposed to in liquid form. and why this helps sustain life. If you've ever dropped an ice cube into a glass of water, you've seen firsthand how the solid form of water, ice, is less dense than the liquid form, right? The ice floats. This is because of the hydrogen bonding in water, and this feature helps support life. Remember, hydrogen bonds are not very strong, and they break and reform all the time. Water molecules move around a lot, and the weak hydrogen bonds constantly break and reform. Because of this, liquid water molecules are very disordered and can pack in rather tightly or close to one another, meaning there are less empty spaces in liquid water. Now, when temperatures drop below 4 degrees Celsius, and we now start to see the formation of solid water, also known as ice, begin to form, the water molecules stop moving around. This gives the hydrogen bonds opportunity to become more stable. When stable, still hydrogen bonds form between frozen solid water molecules. It forms this hexagonal crystalline lattice structure, which you can see has many, many more empty spaces in it than liquid water. These large empty spaces are what make solid water, meaning ice, less dense and lighter than water, which causes the ice to float when it's placed in liquid water. Now, that's great and all, right? Ice floats, and now we know why, but who cares, right? Why does this property actually matter? Let's talk about it. Well, all of these species sure think that it matters. The layer of ice that forms on the top of liquid water in nature insulates the water underneath it, keeping that water that's below about the same temperature, meaning no further ice forms underneath that layer. Or if it does, this happens very, very, very slowly, so it's not detrimental to the beings below. The layer of ice that forms, therefore, helps keep the liquid water within livable temperatures for aquatic life. This is not only important for the survival of organisms that live in water, though, but it is also very important for species that rely on aquatic life for food, right? Other substances become more dense when they freeze or turn into a solid, right? For instance, solid benzene sinks in liquid benzene. Water is special because it is less dense in its solid state, and this is because of hydrogen bonds, and this helps sustain life. So now as a check-in, applying what we just went over, imagine we lived in a world where ice was more dense than liquid water, meaning ice sank in water. So new ice would constantly be forming at the surface of the water and then sink. Why would this be a problem for aquatic species? Check-in number 20. In Colorado, it can be blazing hot during the day, but then get really cold at night. Florida, by contrast, has relatively the same temperatures during the day and at night. What property of water explains how our dry Colorado climate results in such temperature fluctuations? All right, now moving on from the density of water to why water is such an excellent solvent, meaning it's really good at dissolving things. Because of its polar nature, water can form hydrogen bonds with lots of things, and therefore it can dissolve a lot of things really, really well. So let's look at this example with salt crystals that are placed in water. Salt crystals are typically made up of sodium chloride, which are represented by NaCl, okay? So sodium chloride. But when salt crystals are placed in water, water molecules surround individual sodium and chloride ions that have broken away from the salt clump. Now, sodium ions have a more positive charge, so the more negative end of water molecules, meaning the end with oxygen, surround the sodium ion, forming a hydration shell, keeping it from reassembling with the rest of the salt crystal that it broke from. This is the basis of dissolving. And similarly, chloride ions, which have a more negative charge, also have a hydration shell form around them, but because the interactions with the partial positive ends of the water molecules, meaning the hydrogen ends of the water molecule. This is a prime example because salt, or sodium chloride specifically, is a polar and therefore hydrophilic molecule. So it dissolves readily in water because it has a high affinity to interact with molecules due to its polarity. However, water still has significant impacts on molecules even if it can't dissolve them. Let's explore a nonpolar molecule like oil. When oil, a nonpolar hydrophobic substance, is placed in water, the oil droplets all aggregate or cluster together, avoiding the water molecules. We call this clustering of nonpolar substances together when placed in water hydrophobic exclusion. So even though water doesn't directly interact with nonpolar molecules, it does still influence them. And as you'll learn later, the ability for water to influence the shape of something can very easily alter that item's function as well. So now, as another check-in number 21, would you expect the following molecule to be hydrophobic or hydrophilic? Think back to polarity to help you out. Number 22, would you expect this molecule, potassium chloride, to be hydrophobic or hydrophilic? Number 23, below is something we call a phospholipid, which is a substance that makes up the protective membrane surrounding all of our cells, right? If you've ever heard of a plasma membrane, it's made up of these guys. These structures are made up, though, of a hydrophilic head and hydrophobic tails. Considering the properties of water, along with the concept of hydrophobic exclusion, how would you expect a bunch of phospholipids to arrange themselves if you were to dump them in a pool of water? Number 24 and 25. When you go swimming in a lake, you are submerged in and surrounded by water. Yet your body does not absorb all the water that's surrounding you, right? Based on this, do you think your skin is likely hydrophobic or hydrophilic? Number 25, why do you think this property of your skin is so important? All right, A+ work, everyone. That concludes our discussion on the properties of water, which finalizes our discussion on the chemistry of biology. Congratulations!